So welcome everyone. By the way, it's also not a Flink operator, which for those of you who know Flink, it can also get a bit confusing. So hello, my name is Gyula Fóra. I'm a Flink contributor, and my co-presenter is Attila Mészáros. He's a core contributor to the Java Operator SDK and some other related projects. Today we're going to talk about Kubernetes operators, and more specifically about building one for Flink, and you can kind of take it as an example of building a Kubernetes operator for other big data processing frameworks in Java. That's a very important point. So let's start with a bit of context on Flink itself. It's not the most important part of the presentation, but it doesn't hurt if you know what Flink is. Flink is a distributed data processing engine. It processes data on a set of mostly long-running processes that can run in various environments. One of the more popular ones these days is Kubernetes. We have a bunch of Flink workers, and they consume data from batch and streaming sources like Kafka or HDFS or Iceberg, and you do some analytics or transformations on them, and then you typically ingest the data, output it somewhere else, sync it in other words. There are batch jobs in Flink, and there are also streaming jobs in Flink, but at this point in time, I would say you can argue that Flink is best at long-running stateful stream processing. And that's actually the target use case that we're touching here as well. So what does running Flink on Kubernetes mean in practice? So if you don't know the Flink Kubernetes operator yet, then your experience will when you run your Flink job or Flink application, it will look something like this. So a Flink cluster or Flink application deployment consists of a set of Kubernetes resources that belong to it. You will have a few config maps where you store configuration. Some config maps will be used by Flink itself as part of the Flink Kubernetes integration itself to store some metadata for high availability and whatnot. You will have a deployment that corresponds to the Flink master component, the job manager. And then obviously the arguably most important part is you will have a bunch of pods that contain the actual Java processes corresponding to the different Flink components like job managers and task managers. So in this small example, you can see that we have the job manager. The name doesn't contain job manager, but you can kind of imagine that. And then you have two task managers. It's a small Flink application, but of course, if you have large pipelines, then you will have much more pods. And I want to emphasize that this is a single Flink application. So in your Kubernetes cluster, if you're running multiple Flink applications, you will of course have multiples of these. You can kind of select them by their name or labels or whatnot. So this looks fine. You can submit a job, and there are some templates on how to set these resources up. And there's also the Flink Kubernetes integration where through the Flink CLI, you can actually get this quite easily. But this is not where your problems end in practice, because submitting a streaming job is just the beginning of your streaming journey. It's not really where you want to get to. Because for streaming applications, a single job that is running somewhere is not kind of the concept that you are working with. It's a streaming application that is running over time, over a period of weeks, months, or years in a lot of production cases. So a streaming application actually goes through an evolution of, I don't know, hundreds or even more job versions over time that you upgrade and keep running and evolving as you fix bugs, add new features and whatnot. And this is one of the key defining features of Flink, that it allows you to upgrade your jobs in a stateful way without losing data. So how does this actually map to your experience of running this on Kubernetes? Well, you submit the job, you will of course monitor it, and you set up your dashboards, alerting, and then over time you fix bugs and implement some features. And when you want to deploy a new version, you will kind of execute the upgrade yourself. You take a save point, which is Flink's backup or consistency mechanism, and then you shut down the resources, clear all the Kubernetes stuff, and then you resubmit the new one, new pods, new config maps with the new application jar and config. And then you go back to step 2. You again start monitoring, but this never really ends. I mean, if you quit your company, then yeah, maybe somebody else will take this over, but the problem remains. So in practice, before operators, what you would do is you would write scripts for this. You would automate this with Python scripts, and many of you have probably done this before. You have a Python script for upgrading or rolling out a new version of something. But still, you will end up with a lot of low-level Kubernetes interactions. You have to monitor these pods and whatnot. It's going to be hard to integrate with native Kubernetes tooling, because what you have is these pods and deployments, but there's nothing corresponding to the concept of a Flink application on a high level in Kubernetes. This results in tons of duct tape all over the place, and most big users will end up drifting toward one of the commercial platforms that support something like this. So it would be great if we had something that could bring the Flink application abstraction to a Kubernetes level. And this is the point where I'm going to give the word to Attila to introduce the Kubernetes operators.
Thank you. Okay, hi. So I'm going to talk about how to remove those duct tapes in general and how these Kubernetes operators work, mostly in general, and then Gyula will talk about a Flink operator. So in general, what is a Kubernetes operator? To understand that, let's talk about a feature of Kubernetes. You probably already know these built-in resources like pods, deployment, and stuff in Kubernetes. There is a special resource called custom resource definition, which allows to introduce your new type. In this sample, it's a sample from Java Operator SDK, to create an abstraction over deployment of a static web page. And this basically allows you to specify a new kind, define its schema, define if it's namespaced or other properties, and its status, and everything that's needed related to the naming of the resource. If you apply such a resource to Kubernetes, the API is extended in runtime, and basically you are able to create these new instances of these resources that you just defined. So everything just dynamically extended. It works out of the box. You can use kubectl, you can use watches, all the operations, RBAC is working. So everything is fine with your new resource. It's just a little bit dummy, doesn't do anything. It just sits there with a nice RESTful API of Kubernetes. So operator pattern says that we have these resources, our custom resources usually, and we have this other part, it's called controller, where we check those resources and we try to reconcile them against the actual state on the cluster. So in the spec part of the resource, we design or discard the desired state and reconcile it, and maybe write out some status based on the last reconciliation. How does it work in practice? It's basically a controller is a process or a pod in terms of Kubernetes. It checks, the API server checks those resources, and within WebSocket receives all the news or the new events regarding the resource. It's usually the event contains the whole resource. It just cached in the local cache of the process and kicks out or triggers the reconciliation. So if the reconciliation is triggered, your logic in your reconciler, your implementation, it just does its job, does your logic, and possibly updates and creates or deletes some resources in Kubernetes. It's worth to mention that nowadays it's not just Kubernetes resources. There are projects which are managing, we call it external resources, like you can have a representation, for example, a GitHub repository or something, that you create a custom resource that represents the GitHub repository, and that the controller just will create and talk to a GitHub API. So it's fairly common. For example, projects like Crossplane, it manages AWS or Azure or other cloud provider resources from the Kubernetes. So this applies not just for Kubernetes resources, but in general, you can manage any resource with this pattern quite easily. The one point is that all resources are cached usually, and reconciliation ideally works on cached object, and we are caching and receiving events, not just about objects, or not just about custom resources, but all the managed objects and resources. So how to write these in Java? There comes in picture Java Operator SDK, which is quite mature and production-ready framework for quite a long time. We are developing it for about 5 years now. And basically, we see the tendency that people who are implementing these services like Flink, Keycloak, or lots of others in Java, it's kind of don't want to introduce other language to the project, or just want to reuse some libraries in the operators and the controllers. And it's quite handy to then write the operator or the controller in Java. So that's basically the target audience of this framework. And it has a controller runtime of the core framework, obviously, but it builds on the fabricated Kubernetes client, which already brings a lot on the table. So you can just generate the CRDs from Java classes or other way around. It contains the informers, redirection, and all the resources and libraries that Go client or Go counterpart does. And we are supporting integration, end-to-end testing, and everything basically that's handy to implement these operators. There is also Quarkus extension, which is quite, we are putting lots of effort into that, which also puts additional features on the table, and it's really worth to try it. There is a community-maintained Spring Boot starter too. So Kubernetes has also additional it's kind of technologies that are used in combination of operators. I'm not going to detail in that, the conversion hooks and admission controllers. These are the mutation hooks and validation hooks. There is a sub-framework for that in the Java Operator SDK. So just shortly, usually so by default choice, if you are not going from a Java world, the default choice is usually Go, and writing these operators in Go. But compared to this Go counter runtime, called counter runtime, the core library in Go, Java Operator SDK tries to be a little bit higher level, and this batteries included. So that's quite a difference there. We'll get back to that a bit. But the API is really simple. Basically, just this is a low-level API. There is a high level too, but basically just implement a reconcile interface for your custom resource, implement your logic, and maybe patch your status at the end. And you get all your cached resources from the context, and you very easily to register additional watches and resources. So it's really easy to start with. I think it might become more complex after a while, but yeah, the API is really simple in most cases. So I mentioned it's a little bit higher level in the Java Operator SDK. It means that, for example, with out of the box, if you know finalizers in Kubernetes, you don't have to manage those explicitly. For example, for those, just you implement the cleaner interface and cleanup method, and all the finalizer related logic and related stuff is just managed for you out of the box. So this is fundamentally different, like in other frameworks. And basically, that's it from me, a short introduction, and I give back my word to Joel.
Yeah, thanks. Yeah, so we've now seen two somewhat disconnected parts of this whole operator story. So we now know what Flink is, and we have a problem statement that we want to manage these Flink applications in the Kubernetes environment. And Attila showed us that we can actually extend Kubernetes itself with new types of resources, our custom resources. So how does this, how do we connect these? How do we make something for Flink? So this is where the Flink Kubernetes Operator itself comes into the picture. The Flink Kubernetes Operator is kind of built from two parts, so to speak. One is the custom resource definition. That is a custom resource specific for Flink applications. So instead of just having a concept of a Flink job, now we will have that we have to manage ourselves and creating pods and whatnot. We will have a dedicated resource type in Kubernetes that represent a Flink application. So in our case, it's called Flink deployment. There's also a Flink session job. Check the docs and you will find more about it. But basically, a Flink deployment is a Flink application cluster. It's not just a specific job. It's a proper Flink application. You define the specification, the Flink image, Flink version. You put your Flink configuration there, task manager, job manager, high-level resources, and also your job configuration, all in a single nice place. You don't need to create config maps. You don't need to think of how this will talk to Kubernetes and whatnot. And you basically take this YAML, which is the specification of your Flink application, and then you submit it to the Kubernetes cluster. On the Kubernetes cluster, because this custom resource type, Flink deployment, is now available, the Flink Kubernetes operator will pick it up and it will start reconciling it. When you create a new Flink application, it will deploy it as a job. When you make changes to it, if you change the specification and apply it to kubectl, the Flink operator will actually realize that you have changed your Flink application settings. Maybe you upgraded the image. You want to deploy a new version. The Flink operator contains all the logic that is required for executing stateful upgrades of Flink jobs. It will make sure to have clean shutdown of the previous application, store the latest state, and use it to upgrade it. You don't have to code around it and make sure you have your fault tolerance logic inside your deployment scripts and whatnot. It is all part of the implementation, and it's actively developed by a large part of the Flink community. So this is a super convenient way of running Flink on Kubernetes, and the project is also quite mature at this point. We have open sourced the Flink Kubernetes Operator about 2 years ago. So we have around 10, 12 stable releases already with a very large number of users. And I think it's safe to say that this is the way of running Flink on Kubernetes today. So what does it do? Well, the core task of the operator is to manage the application lifecycle, things that you want to do with your Flink jobs. Run it, stop it, delete it, execute stateful upgrades, save point management. You can enable periodic save points, and the Kubernetes operator will keep track of everything, make sure that even if multiple users are taking actions on the same Kubernetes resources or multiple on the cluster, they don't conflict with each other, that things don't get entangled. Also, with now having a Flink-specific custom resource in Kubernetes, we can have a much tighter integration with Kubernetes native tooling. So now, instead of just looking at pods and deployments and trying to figure out what's going on, we can simply look at our Flink deployment resource, because the operator will add the required information to that resource instead of having to gather it from all over the cluster. One good example of this is having proper events associated with your Flink deployment. So whenever there is something noteworthy for the user, the operator sends an event and associates it with the Flink deployment custom resource. So you have a single place to get all the updates and information. Another big part of this is the status of the custom resource, because Kubernetes resources contain multiple parts. Specification is something that you define. This is what you want. And the operator will try to get that for you, reconcile the resource until it matches the specification, what is running on the cluster. But in order to do this, the operator also needs to continuously collect information about the running job. And most of this information is stored in the status field of the custom resource. This is auto-populated by the operator. So when you describe your Flink application resource, you will see the status that the operator put there. And some of these are somewhat internal to the operator logic, but it also has some nice practical user-facing parts. So you can, by a quick glance, look at things like job status, like when was it started, and kind of you can, if you understand what you're seeing, then you can have a quick overview of the health of the running application without having to go to all the different like logs and different resources. Yeah. So this was the last slide. Thank you very much, and we are happy to take questions.